Hello, welcome back. In this video, I'm going to talk about how X-ray and electron beams are produced for medical applications. And I'm going to split this into two parts because it kind of depends on the energy. So the first part, the topic of this video, is X-ray tubes. That's sort of the low energy part of how this happens for diagnostic purposes. Okay, and then in the next video, we're going to talk about linear accelerators. That's the high energy part, which is more in the therapy realm. That's for photons and electrons. Before I get into the application, I'm just going to step back for a couple minutes and talk about some fundamental principles first that you need to understand for this to make sense. Okay, here we go. We're going to start by understanding how a charged particle moves in an electric field. So let's draw two plates here. These are two electrodes. They have some voltage between them, positive voltage here, a negative voltage here. So we're going to connect them together to, let's say, a battery or some kind of device that supplies voltage. And then let's put an electron in here. An electron moves in this field because it experiences some force between the two plates. So it's an electromotive force that makes it be attracted to the positive plate, which is the anode. So there's some potential or voltage, V, that's supplied by this battery, and then there's some energy that the electron gains. The energy is equal to E, the charge, times V, the voltage. So the symbol that we've been using all along, EV, that's it, 1 electron volt. It's the energy that one electron gets moving through a potential of 1 volt. There are going to be some practical applications to this, so let's look at one of them in terms of an X-ray tube. So we're going to talk about the X-ray tube. X-ray tubes are used to make X-rays up to about 200 keV, mostly for the purposes of diagnostic imaging. So I'm going to draw the two electrodes here. The first one has a very particular shape. This is called the anode. And like I drew before, this is at a positive voltage. On the other side is the other electrode. It's sort of a filament wire at a negative voltage. It's called the cathode. So electrons are essentially boiled off the cathode and they move towards the anode because remember they have some voltage V between them. So the electron is going to go this way over to the anode. It's going to hit the anode, and that's where the action happens. So let's zoom in on this anode if we can. If I could go in close enough, I would see an atom like shown here and the electron coming in towards it. As it comes towards it, as you remember, it gets bent around the nucleus, and in that process it's going to make radiation. This is the Bremsstrahlung, breaking radiation coming off here like this. If this is unfamiliar to you, go back and look at video 7.1 on radiative loss. So here's the photon coming out, the X-ray coming out from the anode at an angle like this. And these are the X-rays we see from X-ray tubes. So it's important to understand the design of these tubes and the anode in some detail. So let me go over some points here. First of all, the whole assembly that I've shown here is enclosed in a vacuum chamber. It's typically made out of glass, and that eliminates the air in between the anode and the cathode. And that's good because the air would cause sparking with the high voltages that are involved. And then below the anode is a thin window, usually made of beryllium, and the photons emerge through that window. So the design of the anode is also very important. And there's quite a few things to talk about here, so let's go over those. So first of all, the anode face is at an angle relative to the electron beam. Bremsstrahlung photons are produced inside the anode and coming out in all directions, but the only photons to escape are those that are emerging in the direction of the window. So that's roughly perpendicular to the electron beam. Second, the electrons impact the anode in a roughly circular area. That's called the focal spot. And the size of this focal spot is an important parameter because it influences the resolution of imaging that's achievable. The size of the focal spot is dependent on the angle of the anode because you're viewing the focal spot from below. So depending on the angle of the anode, that determines the apparent focal spot, how big it actually looks from viewed down below. And this is sometimes referred to as the line focus principle. You'll hear that phrase. And then third thing, there's a differential attenuation in the anode itself. That is, some photons are produced inside the anode material, and they have to travel through some material before they emerge. So if that causes some effect on the beam. So if I draw a profile of the dose or exposure, it's not exactly flat. There's a lower flux of photons on the left side of this image relative to the right because they're going through more material in the anode, and this is called the heel effect. And it depends on the angle of the anode as well. Final thing, the choice of material for the anode is important. So a key design goal here is to achieve the highest efficiency of X-ray production that we can. And if you think back to video 7.1, you remember that radiative losses are more efficient in higher Z material versus lower Z material. So that means a high Z material should be used for the anode. Another design consideration is that you're heating the anode. So there are collisional losses of electrons inside the anode, and that heats up the anode. So if you heat it too much, the anode may melt. That would be bad. So if you remember back from video 7.2, collisional losses can be quite large, especially when you're talking about low energy electrons. So it's an important thing. So the first way to address this is to use a metal with a high melting point for the anode. The anode in most diagnostic tubes is made from tungsten, which has Z of 74. It also has the highest a very high melting point, over 3,000 degrees centigrade, so it's a good choice. And the second way to mitigate the tube heating effect is to rotate the anode, to spin it. And if you do that, then the electron spot isn't always impacting the anode in the same region, the same spot, but it's distributed over a larger area, and that helps reduce the impact of heating. So I want to go back here and look at the anode and try to understand the spectrum of X-rays that comes out from the anode. So plotting the spectrum, which is the number of photons versus the energy of those photons, plotted in keV. So it's going to depend a lot on the potential difference between the anode and the cathode. So that potential is, I'm going to write as keV for now, so because it's typically in the kilovolt range. And so the potential, that's going to be the largest possible energy X-ray that comes out. So you can't have any X-rays above this value of keV. Let's say it's 120 keV. You can't have any above that because there's nothing with energy above that. As you go to lower energies, you get more photons out, though, and it kind of looks like this. This is a typical Bremsstrahlung spectrum coming out of a tube. So more energy, more photons at lower energies. Okay, now there's other effects, though. In particular, this tube is encased in a glass casing that's then evacuated to low vacuum. Why is it in a vacuum tube? Well, because these electrons flowing through the tube, they need to go through a vacuum and not collide with air molecules. Also, there'll be an arc between the electrodes because they're high voltage if it has air in there. So it's a high vacuum. And then there's a window here which allows the X-rays to come out. That's typically made out of beryllium. So when you send a spectrum through a beryllium filter, it's going to filter out some of these X-ray photons, let others through. It's more efficient, as you'll remember from the photoelectric effect, it's more efficient at absorbing the low energy photons. So the high energy photons pass through, but the low energy photons do not so much. So the spectrum curves over like this. That's a filtered spectrum going through the window, fewer photons at low energies. Sometimes tubes have more filtration as well. So I'm going to draw another filtered spectrum here. So this is what it might look like if we also send it through another filter. This might be aluminum or copper of some thickness. And as you do that, the mean energy of the spectrum shifts up. It hardens. Okay, now let's go and look at the kV, the potential between the anode and the cathode, because that's going to have a strong dependence on the spectrum. So I've written this as kV, but really usually it's written as kVp and kVp here. So let me explain what that means. So let me plot a little graph of the voltage over time. So this is time and the volts coming in. And what happens is you want a constant voltage like this on the tube, but you can't quite achieve that. You have this little sort of ripple that comes from converting an AC current voltage into DC. And so there's a ripple voltage. And so what we talk about often then is the peak voltage on this ripple. And that's where the P comes from. So the voltage at the peak of this ripple. So kVp determines the maximum. It's a bit of a technicality. So on the tube then you can set two things. You can set the kVp, and you can also set the MA, the milliamps. That's the current coming through the tube, or the number of electrons per unit time. And that will shift the whole spectrum up or down. Setting the kV will shift the maximum energy up or down. All right, so putting this all together then, here's what the spectra would look like. Here's a spectrum of a tube that is set at two different kVp values. One at high kVp and one here at low kVp. And what you'll see here is that the maximum energy changes as you change the kVp. One thing that's kind of useful to know is that the peak energy, the peak energy here is usually at roughly approximately 1/3 of the maximum energy. So if I have a tube set at, let's say, 120 kVp, then the maximum energy in the spectrum would actually be 40 keV. Okay, so that's how you would do a problem like that. So this first spectrum here is actually harder. It's shifted in the mean energy is shifted to a higher energy relative to this spectrum at a lower kVp. So that's changing the kVp. Then the other thing I can do is, like I said, is keep the kVp constant, right? But now I'm going to change the MA, the current, in the tube instead. So both of the spectrum are going to end here at some kVp. And the one at higher current is going to go like this. And the one at lower current, just the whole thing is going to be shifted down like this. Kind of constant shift. This is for changing the current. One simplification and thing I didn't mention is that oftentimes these tubes will actually show lines. So these are the K and L shell transitions, and M also from the material in the anode. And so that means that you're getting characteristic X-rays out of the anode itself, and you can see those in the spectrum of the tube. So you see extra emission at a particular energy corresponding to the K shell transition in whatever metal you're using. And so they actually use that in mammography. They'll actually use the K and L shells, photons, to do imaging, because you get essentially a monoenergetic beam, which allows you to reject for scatter and so on, and get better image quality. All right, that concludes the discussion of X-ray tubes, the basics of it. You'll see it come back again when we talk about imaging in later videos, because of course these tubes are used to create X-ray radiographs, CTs, and so on. They're also used for therapeutic purposes. I'm not going to cover that a whole lot, but you'll see them in systems where you'll have you can have a very tiny X-ray tube inside of a catheter, and that's inserted inside the patient that can deliver a therapeutic dose at low energies. And there's some other applications as well, and we will see a bit of that later as well. I'm going to leave you with a little bit of reading here to understand more if you like. And in the next video, we're going to get into the high energy regime, which is creating photons and also electrons with a linear accelerator. And I'm going to go over that. Thanks.